Got the recording started. All right, hey everybody. Thanks for calling in. Probably, well, definitely going to be a bit of a short class today. My computer and uncle both managed to die yesterday, so I wasn't able to get a notebook put together for the YOLO stuff, just because the laptop I'm on now is can't really handle a lot of OpenCV. It's kind of an old laptop just for like writing and stuff. So if I don't get things back up and running to get a notebook on the repo in the class page for YOLO, yeah, just to give away some of the secret sauce, you can go to ChatGPT and just ask for some YOLO implementations in Python and in OpenCV, and it'll should get you started um, towards finishing the last of the project and kind of give you the code you need. But I'm going to try and get a YOLO notebook together, just kind of for completeness to put up on the site. I do still kind of have all the lecture and stuff ready to talk about YOLO, so we can still go through that, but no code example as of yet. And the other announcement before I go into the slides and dive in, I'll talk about it a little more at the end of the slides, but this is kind of as far as introduction to computer vision is meant to go. We've kind of covered all of the material a couple weeks early. So, like I mentioned at the start of the semester, we got about 4 lectures left. I'm happy to talk about any sort of applications or algorithms y'all might be interested in. We could talk a little more about machine learning. That's kind of outside of the scope of both intro to computer vision and computer vision in general, but I can, go through a lecture on just sort of training machine learning for computer vision type tasks. We can cover that. Or if there's any sort of like 3D stuff, like image stitching or structure for motion, just drop it in the Discord if there's anything you kind of want to hear about. And I can throw some material together for our last couple weeks together. So with that, I'm going to share my screen. And, can everyone see the slides? I'm guessing so. Okay, thanks. Yeah, I'm one tiny screen. I'm used to having several monitors to work with. So it might take me a little while to flip through things. All right. So, like I said, we're talking about YOLO today. And so, like we said, YOLO is you only look once. So, the reason it is called that, what we're going to go through, is because it does look at an image all at once, um, and does not have a key point extraction step or a feature matching step the way SIFT and SURF and FLAN do. What we've talked about up till now, when we're talking about mid-level features, and we've sort of gotten into high-level features a little bit with FLAN, what we've been talking about is this idea of we're extracting a feature, and we're getting a feature vector, and we are having our target feature vector. That's kind of what we're looking for. So we have a feature vector for Kirby, and we have a feature vector for Pikachu, and we are matching those against all the key points one of those algorithms has chosen in the image. Um, what we're doing now with YOLO is it's not finding key points, and we're not seeding it with a source image to find kind of our target feature vector. What we've done so far kind of is, we've found our features and we matched our features. Essentially, What we want to do now with YOLO is try to do that much faster and try to do that with a little bit more accuracy by looking at an entire image and treating it as a regression problem rather than a similarity problem or a anomaly detection problem. So it's a single step algorithm, like I was saying. It's not finding key points, it is finding features. It is a very high level algorithm that is works on a semantic output, which is to say, it doesn't say there's a key point here. It doesn't say, I've matched a feature here. It says inside this bounding box, there is a person or a cat or a ball, if we're kind of going with our classic soccer ball example. Um, so what it does is kind of the steps in which YOLO operates is that it looks at the entire image. It turns that entire image into a grid, and it looks inside each grid cell to determine a bounding box for if there's a feature in that grid cell, the probability that the object inside that bounding box is what you're looking for is determined, and then a confidence score is calculated. So rather than looking across the entire image for changes, like we have been doing this entire time until now through various forms of derivatives and Gaussians and gradients, Laplacians, on and on and on, we've been focused on looking at how things change within an image relative to each other or relative to other images. And that's sort of where traditional CV stops, right? Like I said, we've kind of gotten as far as we had planned to go, or as far as most material covers for an intro to CV class, because when we make this change to YOLO and other machine learning algorithms, we are not looking for changes relative to each other across the image, right? It is no longer a contextual anomaly problem. It is simply subdividing an image into a grid. And then within each grid cell, the algorithm determines, is the feature I am looking for in this grid cell? If it is, how much of the cell does it occupy? And if it is there and it occupies some of the grid, how sure am I that it is there? So this is kind of how it goes with the bounding boxes. Like I said, what you do is you have this grid, and in every grid cell, it makes its own determination as to whether or not the feature is in that grid cell. And then the regression side is it just sort of mushes all the cells back together into an image. And there's non-maximal suppression, like we've used in a lot of other algorithms, that clears out any overlapping bounding boxes. So if neighboring grid cells think they have found the feature we want and sort of draw a bounding box that overlaps across cells, we use non-maximal suppression to clear those out. And so what all this adds up to, I guess kind of what the punchline here is that YOLO is a neural network. So it has to be trained to work. Oh, actually, hang on a second. I'm gonna, all right, I'll turn my video off for a second because I want to try something. I got a went to a yard sale and I got these dry erase boards for $1. And now I'm going to use it because I can. Oh, right. So we have our image, right? And we have like a person, and then there's a soccer ball. And so before, right, Sift or Flan would just look at every place or orb and find all the key points and then match them. So what? So when you use YOLO, right, you're creating a grid, and then every grid square does its little test to see if it has a feature in it or not. Draws a bounding box around the feature when it finds it and does some math, and then we'll say, okay, I think, with some confidence measure, this is a ball inside this image. So that is the main difference between what we've been doing and what machine learning does and the newer kind of algorithms do. So, yeah, what we have to do before we can use YOLO or any machine learning algorithm that is not an unsupervised algorithm. So, and just kind of because you probably have heard these words a lot before, but unsupervised is just you turn on the algorithm and it finds stuff. A supervised neural network means you have trained it before using it, and YOLO is a supervised algorithm wherein somebody takes 10,000 pictures of a person standing next to a soccer ball and then manually draws a box around the soccer ball and says, this is a soccer ball, and manually draws a box around a person and annotates it as this is a person. And then you apply all the YOLO calculations, and that becomes like your feature vector. So instead of a list of key points, it is inside of the bounding box containing the soccer ball, a list of uh, parameters that go into the neural network. Um, and there's a lot of stuff I can talk about later. One of the things about neural networks is nothing inside of them makes sense to a person in any way. When we look at a sift or flan, uh, we can see the key points kind of on the patterns of a ball, or like with the SpongeBob example in the last notebook, that big white highlighted area. We can see that as people and it will make sense. The values inside of a neural network that tell it is looking at a ball is usually just somewhere around 1,000 random nonsensical numbers that would mean nothing to a person. And that is, again, kind of one of the big differences when we make this leap from, you know, treating an image as a self contained kind of piece of information that we can find all of our key points in and work with, to treating subsections of an image as a classification. So, all that to say, before we can use YOLO, somebody has to annotate a big data set that includes bounding boxes around soccer balls, and then train a detection and classification algorithm, in this case YOLO, uh, on the features that make up a ball inside of the neural network. So this kind of abstracts that to sort of the general case of if I'm doing a feature matching, or usually at this point, once you get into the ML side, usually people just talk about object detection classification. We've sort of left behind this idea of a feature or a feature vector and moved into a classification space, if you want to think of it that way, as kind of keeping the coordinate space, parameter space, feature space through line. Now it's a classification kind of space where each grid cell inside the image is essentially testing if the pixels inside that grid cell match the classification information inside of the machine learning model. So in a sense, we're all grown up computer vision engineers now who know everything that kind of got us to this point. And now we're at this point of we can label the data and train an algorithm, and then have it go look for a specific thing instead of a specific vector of numbers. And yeah, so that's kind of what I have for YOLO. Like I said, my computer decided to eat shit and die, so I can't do any real coding examples. But feel free, Chat GPT, Gemini is what I use a lot more of now. I've just kind of gotten more partial to Gemini. Either one of them can, give you a few lines of code to get started using YOLO and OpenCV. And you can kind of take those and apply them to Project 3 and tinker with what you can find and see how well uh, they do kind of on the later part with the Pikachu. And like I said, we've got about 4 lectures left, about 2 weeks. So feel free to drop in the Discord if there's anything you're interested in or want to know more about. I can go into more detail about machine learning if there's enough interest, or like I said, conversely, we can do more traditional CV stuff like structure from motion or autonomous driving. But anyway, let me know. I've got some stuff up on the My courses. I'll put this recording up when it's ready. I just put some good sort of survey papers on machine learning for computer vision, kind of where it started and where it's going. And then if you're more interested in YOLO specifically, I added some stuff about that algorithm lecture series on YouTube, and a pretty cool blog post that goes into a fair amount of detail. So that was what I had for today. Any questions? I've seen a lot of questions about Project 3. I've been trying to answer them as fast as I've been getting them. So do reach out if you're having any trouble or you have any questions, and I'll get back to you as soon as I can. Yeah, what's up?
Yeah, I'm sorry if you talked about this already, but for YOLO on the project, should we be training our own YOLO model or should we be using V3? Because I set it up with V3 and with the Pikachu images, with like the default pre-trained one, it doesn't detect anything. Like all the classes are 0. So,
Uh, that's a really good question that I will go find an answer to.
all right, sounds good. Thank you.
Yeah. All right. Awesome. Yes. Oh, sorry. I thought someone raised their hand. It was just my cursor. My bad. All right. Awesome. Thanks, everybody. I'll get an answer to that question this afternoon, and everybody take care.